right. Okay, we are into circuits now, or current, and here you go. You ready?
Here you go.
We learned several things. We have two objects. This object is positively charged. This object is neutral. They're both conductors. If I connect them with a wire, a conducting path, okay, what happens?
Charge moves from the positive to the neutral.
Electrons go that way.
Ooh, very nice. So charge flows from positive to neutral, or you could say, since we know that positive charges don't really move this way, you could say electrons are drawn off of this one onto this one. Because what really happens, remember, is that this thing has all kinds of charge on it, right?
That's just not the beats.
But mostly positive.
Right? But it has more positives than negatives, right? And so what happens is this draws off some positives over here. I'm sorry, draws off negatives, which cancel out some of these. Let's do another one. And then what we end up with is, if we only draw the ones that don't cancel out, then it appears as if positives have moved from here to here, right? Now, we call this movement, this imaginary movement of positives, we call that conventional current, right? Yeah. Don't forget that. That's conventional current. That's the current that they thought happened, but now that we know what atoms are made of, we realize it's really electrons moving. So in newer physics books, they talk about electron flow, and those of you that have had intro to electronics, is that right?
Engineering.
Intro to engineering, that's right. Did you talk about positives moving or electrons moving? Electrons moving, okay? So like in an electronics class, they'll talk about electrons moving, okay? Now for us at this stage, it doesn't really matter if we talk electrons flow or protons flow or positive charge flow, okay? It doesn't really matter, all right? So we're going to stick with conventional current because that still is the overriding convention that we use, right? So we're going to use that one, not worry about it. What's that? Shh, then quiet down. All right, charge flows. So charge continues to flow
Not until it reaches potentially.
till they reach equilibrium. And what is our equilibrium condition?
When they're neutral.
No, potential.
Until they have the exact same potential. Because when we began, this one had a high amount of positive potential, and this one had no potential, right? And then now, this charge has flowed, emptying this of some of its potential, and building this one up with potential. And once that potential is equal, what happens?
Charge stops flowing.
Yeah, it stops, right? All right, so this charge flow is a temporary occurrence, like a lightning bolt, right? A lightning bolt, boom, it happens, and it stops, right? Yeah, fast. That's why a lightning bolt, in most cases actually, doesn't really kill you. It might hurt you, but it doesn't kill you because it's very quick, and since you're a bag of mostly water,
And you have your suit of armor on.
and you have your suit of armor on, right? That chances are it may damage you a bit, but it won't kill you. All right?
Just a bit.
Yeah, just a wee bit. All right. So that's temporary. How do we keep this going and going and going? Because I want this charge to keep flowing.
Maintain the change in
Put energizer.
The only way to make it happen is to maintain one side at a higher potential than the other. Because remember, the equilibrium condition is when the potential is the same, it stops, right? So I can't allow it to ever reach equilibrium. Does that make sense? Now, in order for you to keep something at an unequilibrium condition, or in disequilibrium, or at a potential difference, so that therefore charge continuously flows, is to have a device called an EMF source. Okay?
That's what it says. There's not something.
Yeah.
You might, did it say EMF?
Yeah.
Thanks.
Yeah, that wasn't supposed to be on there.
It was easy.
Higher curve.
Higher curve. Okay, EMF. EMF stands for electromotive force source. Okay, so electromotive force. So you ever hear EMF? It's electromotive force. That's kind of a misnomer because EMF is measured. By the way, the symbol for EMF is a scripty E. A scripty E, which is EMF, has units of volts. Technically, voltage means a difference in potential. Okay? So an EMF source provides a continuous supply of difference in voltage. All right? So technically, this is a delta V, which is a voltage, right? All right, a potential difference. All right, so now we know from physics that that is not going to come for free, right? So that's going to require a device that's going to consume energy, right? Yeah, you need your credit card to make it happen. All right, so you know some EMF sources. What are some EMF sources? What? A battery is the most common one that you're probably familiar with. So an EMF source is a battery. Okay, what else? A generator. Okay, that could either be a hand-cranked generator or a hamster in a little wheel running a generator.
Or gerbil.
Or a gerbil. Or it could be a generator that is turned by a nuclear power plant or a coal or gas or oil power plant or a hydroelectric plant or a windmill. Okay? Like the windmill farms that they have now out in West Texas. Those are all generators. Okay? Is that? Yeah.
Lights on.
And by the way, if you like windmills because they're advertised as being green, that is true. They are more green, definitely more green
Kill birds.
than a coal or gas or oil-powered plant. However, our existence requires that we destroy something, right? And so that windmill does destroy birds and stuff. So I mean, it's like an electric car. They say, oh yeah, life will be better as soon as we all get electric cars. Yeah, but
Where's the electricity coming from?
yeah, where's the electricity for the electric cars come from? If it still comes from a power plant, then you're a little better off, but not that much better off. So just be aware of that. Okay? So, but all these things that are generating the electricity for our houses, okay? These wall plugs right down here, right? Wall plugs, that's all connected to a generator. Okay, a generator works on what we call induction, which we'll talk about in about a month. All right? Induction is when you take magnets and wires and you force them to go past each other. That will generate electricity. All right? So in every one of these cases, a generator works like this. Okay? In a windmill, what does it do? It spins. So what does it do? It spins magnets past wires. Loops of wires, which generates electricity, or vice versa. They spin wires past magnets. Either way, okay. And then, how does a hydroelectric plant work? Same way. They dam up all the water. The water comes down a tube. It falls past a paddle wheel, turbine, and it spins magnets and wires past each other. Okay. Same thing. All right. How else are you going to generate electricity? You burn oil or gas or coal, okay? And what do with that? They take that heat, they generate steam. Okay, we're back to right? Thermodynamics. They generate steam, and that steam pushes a turbine which spins magnets past wires, or vice versa, okay? Nuclear power plant. Ooh, it's all magical and nuclear-y, right? Not really. What do? They take a reaction, a nuclear reaction. They keep it from going critical. Actually, in almost all nuclear power plants, it cannot go critical and blow up. Not like a nuclear bomb. There's only a few that have bomb-grade material in them. All the rest of them, there's no way they can actually blow up like a bomb. That's not saying that they can't have accidents. It's just they can't blow up like a nuclear explosion.
Which ones can blow up?
There are a few, some of them are experimental ones, and some of them are just really old ones, that's the way they were originally designed. But I don't know now after 9/11 if those have been decommissioned. But there were some test facilities that had bomb-grade material in them. Anyway, so what happens, what do? When the nuclear reaction occurs in a controlled environment, it generates heat. And what do with the heat? They boil water to produce steam, to turn a turbine, which turns magnets past wires, or vice versa. Okay, again, it's all the same. So all these are exactly the same process, all right?
do that manually.
Or you could do it manually. So you could go down to the nuclear power plant and say, look, you know what, I'm going to try and save the environment. Just give me a big hand crank and I'll crank that sucker all day. All right? But you would not get very far.
Well, not me, because they're going to.
Are you all right?
You were very Hulk-like there for a minute. All right, so all these are generators. These all work by induction.
I'm a sexist.
All right, batteries, on the other hand, are not a generator. So how does a battery work?
A chemical reaction.
Yeah, it's a
That
chemical
spins magnets.
reaction.
Has a little magnet inside.
Stick it to your refrigerator.
Okay, a battery works by a chemical reaction. Okay, how long do these generators work? Well, as long as there's wind or water or oil or gas or nuclear stuff to burn. All right, there's a heat source. It's a heat source or a mechanical source like in a windmill or a water wheel. Okay, a battery. Batteries is good until the chemical reaction runs out. Okay? So, now, you look in the back of your calculator, right? So you get your calculator out, you pop this thing off, you got batteries in the back, right? They're little bitty batteries. Okay? And they're hooked up in series, and we'll talk about that a little later. All right? But if you want this thing to run longer, you put bigger batteries in here. And it would run longer. Okay? These are hooked up in series, and we'll talk about this. Each one of these batteries is 1.5 volts. They're hooked up in series, so that's, you add up the voltage. So that's 6 volts. So you know you can go down to the hardware store and you get one of those lantern batteries. You all know what a lantern battery is? Not all of you probably do. But a lantern battery looks like a block.
Oh, yeah.
And it's got these little curlicue things on top.
Yeah.
Right? You can get a 6 volt or a 12 volt. You get a 6 volt one of these suckers, hook it up to your calculator, that will never run out. You could will it to your children and their children. And that thing won't run out. Okay? Because it's got a whole lot more chemical reaction in it because it's filled up with more stuff. Does that make sense? So if you want your calculator to run longer, just hook it up to D-cell batteries instead. Of course, then you've got a great big honking calculator, right? Big heavy thing, right?
Pocket calculator.
Hey, you know what? You could hook up your calculator to, well, car battery's 12 volts, right? We'll figure that out. That's one of the things we'll figure out.
Just hook up 2 calculators.
Yeah, 2 calculators.
If you hook up your calculators in series, maybe.
Yeah, that's...
What?
We'll figure out how to hook up a car battery to your calculator and not blow it up. Okay?
Okay.
But not yet. That's in a couple days. All right. So that's a chemical reaction. So this voltage difference, this energy for this voltage difference occurs in a battery by a chemical reaction. When the chemical reaction runs out, then your battery's dead. Actually, it's a little more complicated than that, which we'll talk about it later. All right? It's called internal resistance of a battery. Okay, there's another way that you are commonly aware of to generate this EMF.
What was that?
A solar cell or a photovoltaic cell.
Yeah, that's right.
Okay? A photovoltaic cell works on a process called the photoelectric effect, which we'll talk about near the end of the year. Okay? We'll put this down. Photoelectric effect. Now the photoelectric effect, everybody, takes light energy, energy from photons of light, and converts it into a potential difference. Okay? So those are our three major ways that you will be familiar with and can use. Now, when we draw one of these on in a circuit, we don't really care which one it is at this point. Now, when you get farther into electronics and all, it may make a difference. But for us, all of these are going to be that symbol right there. A battery symbol. Okay? A battery symbol. We're just going to use that to designate a generator at this stage of the game, or a photovoltaic cell, or a battery. Okay? And the battery will look like this, and we might put EMF is 6 volts. So it'd be a 6-volt battery. And there you go. Now, it's important you know which side's the plus side.
Long side.
That's the plus side, and that's the minus side. Okay? So, if I wanted this charge flow between these spheres to continue forever, or at least until I run out of energy, how do I make that happen? Well, I just hook up an EMF source to it. So, this thing is dead, but what I'm going to do is I'm going to hook up this battery, and this battery has a chemical reaction that makes this side more positive than that side. Okay? And it provides, in my case, a 6-volt EMF. Now, did I tell you how many volts the positive side is?
No.
Did I tell you how many volts the negative side was?
No.
Did I tell you? What did I tell you? What's 6 volts? That's the difference between the two. Okay, we don't know what the plus side is or the minus side. We just know that this thing will force this side to be 6 volts higher than that side. So if this was minus 12, what's this?
Minus 6.
Minus 6. If this one's 0, then this is 6. If this is 3, then this is 9. All right, the difference between the two will always be, until my battery is dead, 6-volt difference. With the plus side 6 higher than the minus side. Okay? Or the minus side 6 volts lower than the positive side. Whichever way you want to think about it, it's the same thing. All right? And so, therefore, it's going to force this side to be more positive than that. And so charge will continue to flow. Because remember, by contact, if I have a battery and I hook this side over to this thing right here, charge is going to flow from this side of the battery onto this until when? Until equilibrium. Until this side is the same potential as this, right?
Yeah.
And then when I hook this one over to this side, they're going to share charge until this is the same potential as this, which means I've created a delta 6 volts. My voice is changing.
I know. I tell
We have a couple competing things going on. Number one is, hey, what if I'd hook this thing up to 60 volts instead?
What kind of case?
Would that be better than this? What would be the difference?
Depends. It makes it.
It might be. It might kill you.
What do you want in there?
All right. If I make this a higher and higher volts,
Okay.
well, let me work backwards. Maybe this is better. What if I make this lower and lower volts?
Less charge. There will be less of a
Less current.
difference.
There'll be less incentive
so
for
there-
this, right?
So
Does that make sense?
Less, will be less able to do work.
The more voltage difference you have, the more energy you have available to do more work, and the more likely you're going to get charge to flow, right? Okay. Let's talk about, well, and there's a competing thing to this charge flow. We're making nice here and saying that the charge will flow and there's no friction, resistance, anything, all right? In reality, what we have is two competing events. We have an EMF or a delta V, a voltage difference, which pushes the charge. And then we have resistance, electric friction, you could say, which hinders the charge. Resistance wants to stop the charge movement. Yeah, so the deal is that we have these two competing things going on at the same time. And the competition between those two will determine how much of this we get, how much charge actually flows. All right? How quickly this occurs. Right? So the bigger the electric potential difference, the EMF, the more of this you'll get. The bigger the resistance is, like the worse the conductor is, then the less of this you'll get. Okay? All right, so let's talk about this thing we call current. All right? We already know EMF. EMF is a delta V, which is a voltage source or a potential difference. All right, so there's number one. Number two is we have current. Current is the movement of charge. Okay? Excuse me. Movement of charge. Now, unfortunately for us, the symbol for current is I.
I see.
I don't know where I came from. It's possible that C was already taken for Coulomb or speed of light or something. Or it could be that the native language of the person that originated it, or sometimes it comes from Latin or Greek or something. I don't know the particulars of where I comes from. All right? All right, so current is I. Current is defined to be the amount of charge moving past a spot in a certain amount of time. So it's the rate at which charge moves. Okay, Q is charge, remember, so it's the rate at which charge is moving with time. All right? So, literally, what's its units?
Coulomb per second.
Yeah, it's a Coulomb
What's it?
per second, which we call an ampere. Named after Ampere. Oh my gosh. But you can call him Mr. Ampere. But for those of us that know him well, we just call him amp. Okay? So the unit is an amp. Okay? The unit is an amp. And the symbol for amp is A. So like for instance, let's go through this. If that's a Coulomb and that's a second, then let's say 3 coulombs of charge go past a spot in 1 second. That would be 3 amps. And the symbol for amps is capital A. All right? Now, because most students are pretty good with their units in mechanics, meters, meters per second squared, seconds, newtons, joules, and all that, you usually do pretty well about tacking those units onto things. But when we get to electricity and magnetism, you need to start making sure that you put your units on. And for some of you, you're going to need to keep a running total, a running list of what your different units are, because you don't use them as often. Now, some of you that have played around with electronics, this is no big deal, but for those of you that have not, then make sure that you really think about what kind of unit goes on these, all right? Make sure you put the unit on it, because you probably won't get credit on the exam if you don't put your unit down. All right, they're getting real sticky about that on the exam. It's a shame if you put down the right number and they don't give you credit. All right, so make sure you put your unit on. All right, so that's current. Now, real quickly, the difference between direct current and alternating current. All right, when you have a battery, okay, we have what's called direct current, because this side of the battery is always positive and this side of the battery is always negative or lower voltage than the other side. Then what happens is if you take a battery and you hook it up to a TV set, then the current is going to flow by conventional current. Which way will the current flow through the battery?
Positive and negative.
Right to left, left to right, up, down, which way?
It's positive.
Clockwise. Right. Clockwise.
Negative.
Conventional current. Positive, around to negative. Now remember, we're assuming conventional current. Now the electrons would flow
From
The other
negative
way
to
around.
positive.
negative to positive. Okay, but we're talking conventional current. It's going to flow this way through. So if they ever ask you a question about which way is the current flowing through this particular resistor,
Think conventional.
think conventional current. Okay, unless otherwise stated, they just ask for the current, always think conventional current, positive to negative. All right? All right, now, there is another way to supply current. Okay, now, first of all, I want you to realize something really important. Does the battery supply the charge that goes through your TV set?
No, there's already charge on there.
No.
Okay, this is really important. The TV and the wires it's connected to are made of atoms. Atoms are made up of protons and electrons. So all the charge you ever need is already there. Okay? So this wire right here, when I plug it into the wall, all the charge I ever need is already in here. Okay? So what do we pay for when we pay our electric bill?
Voltage difference.
We don't pay for the current.
We pay for voltage difference.
Yeah, we pay for the ability to make these suckers in here move.
God, they're just strange.
Right? So they charge us to make them move. Okay? Now when you hook them up to a battery, they all move in one direction. Okay? So what the battery does is not supply the charge. What actually happens is when you hook this up to the battery, they all move at the same time. Okay? Let me show you. Hooked up to your thingy. Thingy-majiggy. Here's your plus side, here's your minus side. Okay. This thing's all filled up with charge. And already we know I'm making a lie because I'm making the positives move, but we're okay with that because we're just assuming conventional current.
It's also morally depraved.
So what happens is this plus and this plus, as soon as you hook that sucker up, these repel each other. So this one tries to move that way. This plus is attracted to that minus, so it's attracted this way. And look, this one then pushes on this one, which pushes on that one and 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 that one, which pushes that one in, which pushes that one out. But wait a minute, as soon as this one moves this way, that leaves a hole for this one to move into. Does that make sense? So the whole thing, as soon as you hook it up, the whole thing moves. Actually, I guess I got it moving, yeah, that way. Right? They all move at the same time. It's like if the whole way when it's really crowded sometimes, you're trying to move forward, but there's people in front of you, The only way for you to move forward is for them to move, right?
Push them aside and then move them.
Knock them against the wall.
Either way, they still have to move.
Yeah.
Yeah.
You move them or something.
One way or another, they gotta move, right?
Yeah.
And if somebody's behind you trying to go forward, then you gotta move.
Elephant
Alright.
comes by, everybody.
Think of the wire as being like a straw, and that straw is filled up with a whole bunch of little BBs. You know what a BB is? Ball bearing, little bitty ball bearings. And if you tried to shove one more BB into the end of the straw, one's going to pop out over here, right? Because there's
They'll
just,
all just kind of fall out.
they're all going to affect each other, right? Okay, so as soon as you flip the switch back there, all the electrons, all the charge in the wires, they all begin to move. All at the same time.
You turn it off, they stop.
Not quite the same time.
Turn it off, they stop. Okay, Mr. Smarty Pants, not all at exactly the same time, because what happens is that information transports itself down the wire at the speed of light. So, there is a slight time lag for which we can't tell, so we say it's all at the same time. Technically,
Unless it's
though,
a very,
there-
very long wire.
Even then.
so it's all at the same time.
It's a wire from the sun to earth.
Yeah, 5 minutes. It may be. Yeah.
All right. Now, so now we have current. Our last thing we need to know right now is that thing called resistance.
You never explained alternating current.
Oh yeah.
Oh, yeah.
Okay, direct current.
It's not important.
DC, direct current. Generators produce alternating current, which is called AC, alternating current. What happens in a generator is when you spin the wires past the magnets, it generates electricity in one direction, and then as it flips past 180 degrees, actually I guess it's 90 degrees, it starts to generate in the opposite direction. And so what you get is current. When you plug things into the wall, the current comes out, and then it comes back. They give you an electron, and they take it away. Give you an electron, take it away.
So it's like if you have a string, you just pull it back and forth.
Yeah. So what happens is exactly. What's really crazy about alternating current is that the charge comes in and then goes back out. Charge comes in and comes back out. So the electric company never gives you any charge. All you pay for from the electric company is for them to make all the charge in this wire
Move back and forth.
go back and forth. Which seems kind of silly, but that back and forth motion is energy, right? And that's the energy that we use to make things happen, like the TV to go on, the lights go on, and all that. Okay, so that's what we pay for from the electric company, is the ability to make our electrons vibrate back and forth. All right? Okay, so resistance. Okay, let's see if you can figure this out. If I had a wire, and I'm just going to draw a picture of a wire up here. Here's my wire. All right, there's my wire. And this side of the wire is a higher potential than this side. So current is going to flow this way. All right, from high to low. Higher to lower, right? Okay, how can I make that wire so that it will have less resistance to this flow? What can I do?
Add a resistance.
No, I want to make it easier.
Oh, you said easy.
How can I change the wire?
Short. Well, assuming.
Make it
Increase.
I could do what?
make it thinner.
Make it thinner? Okay, if I make the wire thinner, will that make the current easier to flow or harder to flow?
Harder.
Well, it's harder because it's bigger.
Less area.
Less
So if I
power.
want less
You actually make it
resistance,
thicker.
this one's going to have more resistance than this one, right?
Yeah.
Okay, so the thinner the wire, the harder it is for the charge to get through.
Yes.
Excellent. Okay, what else could I do to make the charge flow easier or harder? What if I make the wire like this? What if I take the wire
Make it clear.
and I make the wire like this?
Make it clear.
What do you mean?
I thought we could play with
Now, does the electron care if it's wavy?
No.
No, but what the electron does care about is now I got to travel a longer distance, right? Would a longer distance make for more or less resistance?
More.
It's more. So as the distance goes up, resistance goes up. As area goes up, resistance goes
Down.
down. Okay, so that would make for, so you want your wire to be short and fat, right?
On to funny kids.
Something else. What do you want your wire to be made of?
A good conductor.
Yeah.
Something.
Not an insulator, right?
Gold.
Silver.
Actually, I think silver is the best conductor.
Yeah, but what's the
Gold,
negative
yeah,
side
silver,
to it?
gold, copper, aluminum are all way up there.
Copper is
Well,
most
copper's the
amazing. It's
cheapest.
the cheapest.
Yeah, copper, while it's
So
not the
expensive.
best conductor, it has lots of good qualities. One is it's very malleable. Number two is corrosive resistance. Number three
Very
is
cheap.
its expansion and compression. While it heats, it's not as great as aluminum. Aluminum it expands and contracts a whole lot more, like twice as much. So it's more likely to cause a short circuit. And of all the really good conductors, copper is by far the cheapest. All right? Yeah, so you don't want to make your wires out of silver, because silver is expensive and it's corrosive. So you make them out of gold, because gold doesn't corrode, but gold is really expensive, right?
But it's worth it.
Well, in some cases, gold is worth it. So like, for instance, if you have a spot where you're not going to make a connection for a long time, and then once every 5 years you're going to make a connection, and you want that connection to work every time, like the connection in an airbag, right? You don't want the airbag to ever go off, but when you need it, you want it to go off.
Quickly.
And so the connectors would be made of gold, or not really made of gold. They would have a gold coating on them, right? So yeah, if you want to get rich, you steal your airbag out of your car, you scrape the gold. It's not going to be very much. It's only like several atoms thick, the coating. So it's just enough so that they won't corrode, right? Or let's say that you're in a bad caustic environment, like on a ship, seawater and stuff. That's very corrosive, right? So you want your connectors to be gold coated, so that when they connect, they're not like copper, which is going to get that green coating on it. Green coating like this, right? If the copper gets a green coating on it, it's not as conductive, right? So if it's a high quality connector, or it's a connector that you need, it's not going to be connected for a long time, you're worried about corrosion, then you want it to be made of gold, all right? But otherwise, copper is usually the best. Aluminum is cheaper than copper, but aluminum, you don't want aluminum wiring in your house probably. That could cause a fire. But they use aluminum, I think, in high tension wires, if I remember correctly. I'm not sure, because it's cheaper.
All
right. So, diameter? No, that's distance, the length, the cross-sectional area, and what the material is made of. So here you go. Resistance. The resistance of an object. Resistivity, length over area. I believe that's correct. Let me
That
check.
looks like road.
Is that
Yes. All right, now, let me write them all out. R is resistance. R, resistance. Rho is not density. They recycled it. It's resistivity.
Anywhere they want.
But that's so confusing.
I know, it's confusing.
They don't care about
L is the length.
L is the length,
So that's our stupidity.
and A equals the cross-sectional area.
Really? Your face.
So guys, I'm making the
Cross-sectional.
discovery of the century.
CR. No wonder I didn't look right. I forgot my R.
Bag of Sour Patch Kids.
Cross-sectional area.
Sour Patch Kids.
All right? Now, let's talk units, everybody. Length is units of meters. Cross-sectional area, that's this.
Square.
Did you use
That's meters squared. Okay,
unframed?
resistance has a new unit. It's units of ohms.
What home?
All right, the unit is ohms,
How's it different?
named after ohm.
How is that new?
Well, yeah, you had it in pre-AP. That's right.
It's not.
It's new from meters and new.
I mean, not, to him it's new. Isn't it?
That's right. I never heard of it before.
It's just pulling out of my brain just
It's
now.
measured in omegas.
Did you see his eye?
All right. So what's resistivity got to be in?
Oh. Ohms per meter.
Okay, so this has got to be in ohm meters, right?
Where they viewed that?
So if the meters cancel, no, so the meters cancel what that means. Get it with ohm. So this is in units of ohm meters. All right? Now, in your book, there is a table of resistivities. All right? And what you'll find is that gold, copper, okay, metals have a resistivity really low, like E to the negative fifth, sixth, something really tiny. Okay? And then you go and you look at glass. What?
Carbon.
Carbon? Oh, carbon's actually somewhere in between. So you look at glass. You look at porcelain. You look at rubber or mica. And all these, the resistivity is like 10 to the 6th. Really big. Okay? And then there's a group in the middle. Okay? These things that have really low resistivity, what do we call those?
Conductors.
Conductors. The things with really high resistivity, call those insulators. Okay, and then there's a group in the middle, like carbon and silicon, germanium. Okay, all these ones in this special area of this chart.
Semiconductors.
Yeah, all these in this area. Semiconductors. Okay, metals, conductors, non-metals, insulators, in-betweeners, semiconductors. Semiconductors have a resistivity somewhere around E to the 10, E to the 2 to E to the negative 2, somewhere in that range. They're in this Goldilocks area. Okay, semiconductors are really no importance to us except for electronics. Okay, now the reason why semiconductors are nice is because in a conductor, if you produce a potential difference, all the charge just goes whoosh and it moves. All right? If I charge up a balloon on a cat and I just walk past a piece of metal, all the electrons on the outside of that piece of metal whoosh, they move as I walk past. Okay?
So it can't.
That's a problem because you can't keep track of them, you can't control them. In an insulator, you can't make them move at all. But in a semiconductor, you can make them move and control them on a one-by-one basis. So they can control exactly where one electron moves.
Dang.
And that's important because that's how we get our computers to work and our
That precise?
cell phones and all these semiconductor things. Okay?
Are they that precise?
They can get that, they've gotten that precise, where they can control individuals now. Now, I don't know if that's in any production devices yet, but yes.
Just in stuff for like super fighters and
That's the
stuff like
concept of
that.
everything like computers and like
What's that?
that. That's like what like the concept of everything like
Yeah, so like being able to control exactly where they go allows them to set up logic gates and all these different things that allow them to build computers.
Okay.
Okay? So that's the importance of semiconductors. Now, on the way other end is the superconductor. And that's really all metals if you get them cold enough, and then a lot of other materials if you get them cold enough, then they'll have no resistance whatsoever. Okay? All right, but they have to get really cold.
Temperature.
What's that?
Why doesn't our formula account for temperature?
Ah, good question. Good question. You notice this formula only accounts for the geometry of the object and what it's made of. All right?
Major effects.
Now, in reality, these three things are the major effects. They are not the only effects. If you would graph resistance, or really resistivity versus temperature, what you'll find is that the resistivity decreases with temperature until you reach a magical point, like in a metal, and it drops to 0. And that's the critical temperature where you reach what's called superconductivity, where there's no resistance whatsoever. Okay, current is directly related to the potential difference. And it's indirectly or inversely related to the resistance.
Yay, something
Okay.
new.
Now that's Ohm's law. Okay, and that's the way I'd prefer to you to think of it, but nobody likes to think of it that way because it's got a fraction in it. The way you will normally see it in a book is this way.
V equals IR.
V equals I.
Big deal.
Did it change it? V?
Now, here's the thing. There's a couple things about this. The first thing is if you want to write it this way without the fraction, that's great. Okay? Because a lot of students don't like the fraction, books don't like the fraction, it takes more ink, believe it or not, and it takes up more space in the paper, so everybody likes to write it this way. However, remember that this, that's the one that's being affected by the other two. Okay? You gotta remember that. Alright, now, the other thing that is really bad that they skip is this thing right here. They skip the delta. And I don't know why they do that.
They're lazy.
Because it's not a potential at some spot in space causes current to flow. There has to be a difference in potential between two spots, right? So I would like for you to remember to put that little delta there to remind you that there is a difference in potential between two distinct locations. And without a difference in potential between two distinct locations, you will not have charge flow. No current. Okay? Got it? Okay. Just as a segue, side note, real quick. Segue, side note. You remember from last unit? Our good friend V equals Ed. Remember V equals Ed?
No.
Yeah, I do.
I do.
Yeah.
It was delta V, was that?
Yes. Delta V.
Average.
And there was an average here.
Yes.
Okay, remember that? All right. I want you to remember that the electric potential is connected to the electric field. And so, by the difference in separation of the two the potential difference. Okay? So everybody, I want you to think of circuits in another way that you probably haven't thought of them before. When you set up a circuit with a battery, this has an EMF, which is a delta potential difference, right? If there's a potential difference and there's a distance, then that means that this thing sets up an electric field
Inside.
inside of itself. And this should make sense. If I want charge to flow around, how do I get a charge to move?
Create.
I create an electric field which supplies a force to it, which makes it move. Right? Okay? So when you hook this thing, this battery up, what you end up with is you end up with a positive side and a negative side. So wait a minute. How does an electric field work?
Positive.
If I had a positive and a negative, what would an electric field look like?
From positive to negative.
You would go out of the positive and into the negative, right?
Yeah.
Big delta.
But we have a conducting path here. So how does our electric field work?
It'll follow
It
that
goes
line.
out of the positive, and our electric field
Or it's the conductor.
follows the conductor. And our electric field goes through the conductor along the path. That's why our battery causes charge to flow in the conductor, but not outside here. Right? Because the electric field is concentrated in the path. Okay? So if you want charge to flow, you must set up an electric field in the conducting path, and so you do that with a battery. Now we normally talk about it in terms of the potential difference, but that sets up an electric field inside there, and that's why those charges want to move. Does that make sense? All right. Ohm's law. All right? Ohm's law, which will be one of our big laws. So let's start listing all of our equations. Why don't I just start it right here? Our equations will be, so far we have this one. Current is defined to be delta Q over delta T. It has units of amps. Amps. Okay, and we have resistance equals rho L over A, and that's in units of ohms. Okay? Actually, I'm going to write this instead of just writing amps, I'm just going to write A, because that's amps. Okay? And now we have Ohm's law, which is delta V equals IR. Okay? So there's our three equations, of which Ohm's law is going to be a real big player.
Play it.
Okay, so I'm going to skip power and I'm going to go straight into, let's start actually drawing some circuits. So we don't have to cover power. We will cover power. You just got to remind me. Okay, so I need a black marker. Okay, now let's start using this stuff. So we need to know what's called schematic symbols. So here we go. Everybody, you ready? What's that?
Battery.
A battery. What's that?
Two batteries.
Okay. Actually, you know what?
It's two cells.
That's a battery. Technically, that's a cell. All right? Hey, technically, what you put in your calculator is not a battery. It's a single cell.
But put it in series to make it.
When you put several of them together, it's a battery. Okay, we'll just call them all batteries. All right, but technically speaking, that's a cell and that's a battery, but we don't really care. All right? We'll just say this. It's an EMF source, right? Woo! There you go. Hey, if you happen to see one that looks like this, with a little arrow going through it.
Run.
No, it would be a battery that you can change the voltage on. Now, normally for a battery you can't do that, but just in case you ever see one like that, it's one where you can change the voltage. Okay? In the lab, have you ever seen a power supply where you dial it to different volts?
Today.
Yeah, that would be like that. Oh, you're doing that lab today? Or you just...
What?
Nothing? Hey, what's this? What's that?
It's a conductor.
Short circuit line.
Yeah. It's a line, otherwise known as a conducting path, otherwise known as a wire. Okay? So a wire. Wait a minute. What's that?
Switch.
A switch or a disconnect in the wire.
Are we supposed to remember these?
Huh?
Yes.
All right, what's this? That's a
Two
capacitor.
parallel lines.
Now I want you to notice, is a capacitor a conducting path?
Well, now.
Sort of.
Capacitor.
Not really. There's an insulator in between, right? So can you have continuous current through a capacitor? Not direct current. So anytime you see a capacitor, the current will not continue through it indefinitely. It will build up to its full, and then it'll quit. Remember we talked about that with the capacitor? When you hook the thing up, the sides charge up plus and minus. But once it's the same electric potential as the battery, it quits, right? All right, so a capacitor. And these are batteries. All right, what else am I forgetting? I'm forgetting something. Oh, what's this?
Resistor.
A resistor. All right, now, a resistor is a device, a true resistor is a device that converts electrical energy into thermal energy. Okay? So what it does is it eats up the electrical energy, consumes it, and converts it into heat. So where in your house do you have some of these?
A heater.
A heater.
What if you have like
The really, really old ones.
Is that what other things are like?
A boiler.
What's a heater?
Yeah, like a boiler. You have a bunch of these in your kitchen.
Microwave.
Not a microwave,
the
but a stove and a range top.
well, see, that's if we run like we're all gas.
Yeah, we're
Now, if you're a gas household, you won't have these. Because what you do in a gas household, you turn chemical energy into heat, right?
Yeah.
So if you turn electrical energy into heat, if you open up your oven, you'll have a big coil in the bottom. That's the resistor coil. Okay?
A toaster. People have.
Toaster. There you go. A toaster. All right. A bunch of you have this. I would say all girls for sure have one of these.
Hair dryer.
A hair dryer.
Isn't that quick?
Because you can turn it on cold, right? And it just blows air through. But you turn it on hot, and it's got toaster coils in there, which heat up the air as the air goes through.
Oh,
Right?
yeah, I see it. I see it. Now
Right?
you can see the little lines on the toaster too. That toaster.
Yeah.
I'd be like,
Now the lines in a toaster get hot enough to glow.
yeah.
The lines in a hair dryer
A little.
don't get that hot,
But they-
probably
they glow a
because you
little.
don't want to catch your hair on fire. Why
Maybe
not?
I do.
I mean, that's the new
No.
style.
Oh, that happened to that one chick. Did you see?
And no.
Okay.
Yeah,
She got so excited and she said, "Never mind."
the coils in a hair dryer don't get hot enough to burn your hair, although they can smolder them pretty bad.
They're forced to
They
change
can melt them and make them smell nasty. Okay.
Oh, that's how I got this.
Okay, if you see one of these, resistor and a resistor,
You can change the resistance.
you can change the resistance. So I believe this one's called a rheostat, and I believe this one's called a potentiometer. Now, for those of you, a lot of you have these at your house, you don't realize it. A lot of times this is called a volume knob,
Oh.
A volume knob.
or
We don't have that.
some of you, I know, most, yeah,
What's
I
the
ain't got
bottom?
no knob.
What is the bottom one called?
All right, I believe this one's called a
The
potentiometer,
bottom one.
and I believe the bottom one's called a rheostat.
That
Rheostat.
channel?
Statistic.
That channel?
Okay, it doesn't really matter what the name is. If you happen to see one of those, it's one where the resistance can be varied, and so you don't know what the resistance of that resistor is. Like for instance, this one might be listed as, well, that's a 100 ohm resistor. This one might have a range. It might be from 0 to 10,000 or something, just a range, depending. Now, a lot of you have these in your house. Hang on. They're called a dimmer switch. Okay?
We don't have
If you have one of those dial dimmer switches,
You have the
or a slider dimmer switch,
slider.
Turn it.
okay?
Or you have the real old houses with thermals that way.
See this one right here?
Yeah.
The knob that I broke off? That's a potentiometer. That's a variable resistor. When I say change the resistance, it changes how fast this
That
thing
one
moves.
down there too.
Okay? Sorry, Rudy, you had a question.
Although I had a question about it. It's like my heat, like a little heater I have.
Yeah, it's got a knob, and the knob changes the resistance, so it changes how much heat you get out.
Yeah, and then the light, I can dim the light to set the mood, you know. Yeah, so,
Hey, don't look at me when you do
feel like eating.
it. Rudy. Rudy.
Eating cereal by myself on my own.
But you got mood lights, so it's all good. All right.
He sits down on the table.
All right, what's that?
Diode.
No, a diode looks like
That's one of those twinkie
this.
things that
That
has this
looks
thing.
like a light bulb.
It's a lamp.
There you go. It's called a lamp or a light bulb.
Okay,
Light bulb.
that's what it is.
Yes. Now, here's a really good point. The question was, does that light bulb have resistance?
Yeah.
Listen. Listen. All right, this is important. because we could come up with all sorts of different diagrams for like a TV and the iPod and for all these other things, in general, at this stage of the game, here's what we do. TV, toaster, iPod. Because what do all these things do? They all resist current flow because they're all consuming the electricity and turning it into something else, right? A toaster turns it into heat. All right, so a toaster literally is a resistor. Oh, sorry. The TV,
Label them, sir.
all right, sorry, the toaster literally does turn it into heat. The TV turns it into light and sound, right?
And heat.
iPod.
And some heat.
And the iPod.
Okay, an iPod turns it into light and sound as well, right?
A little heat.
Okay, so the deal is
Whenever
this,
it gets too hot.
is that instead of drawing a different symbol for each one, in general, what we'll do is we'll just all consider them to be resistors because they consume the electricity, the electrical energy, and they turn it into something else. Okay? Now, occasionally you'll end up seeing things like this. Like they'll go, hey, that's a clock. And hey, that's a radio. Okay? And they'll do that. But remember, each one of these is just a
Resistor.
resistor. Okay? And a light bulb. This is really important, so I'm glad you brought it up. A light bulb is just a resistor. Literally, it actually is just a resistor that gets so hot it glows.
Like a super.
Like an incandescent bulb. Now, these bulbs are not that way. These are fluorescent bulbs, and the fluorescent bulbs,
Gas.
yeah, they have a gas, and we'll talk about how they light up. They light up because the electrons jump between the electron shells. Okay? Yeah, you learned that in chemistry. All right? And so that's a different way of lighting up. But that's not the same as a regular incandescent bulb, which hopefully in your lifetimes will cease to exist and we'll just have these because they're a lot more fuel efficient. Okay? Or actually, in your lifetime, you'll go to LED lights.
Those are
Yeah, they're, but right now they're really expensive. So for most cases, they're not worth it yet.
We're gonna go back to candles.
My TV is
Candela.
It's forever to turn on though. Like, I turn on TV,
All right.
it's Big B.
Everybody, what's this?
What do you have? Vizio?
Around.
Okay, a ground. And the important thing about this is, here, look.
Struck by lightning.
Do you see this? And I have a 9-volt battery. And if I asked you, what's the potential right here? You would say, I don't know. And if I asked you what's the potential over here, you'd say,
I don't know.
I don't know.
I don't know.
But you would say that what's the difference between those? You'd say 9 volts. Now, wait a minute. If I take right here and I connect this to the ground,
The difference is 9.
wait a minute. Is the difference still 9?
Yes.
But how many volts do I have on this side?
0.
Yeah, that's 0 volts. And over here, now I have 9. So the importance of a ground in most cases is the ground causes a spot in the circuit to be 0 volts. Now that's really important when you're hooking electronic equipment together.
Exactly 0? Or like 0.000000000?
What we define to be 0. Actually, the Earth, I think, is actually a slightly negative. I don't remember. But it's our biggest reference point. So we call it 0. Now, when you hook electronics together, it's very important that they have a common ground, that they're both hooked to the Earth, because otherwise you could hook things that have a potential difference of 120 and 120, but this is 120 down here, this is 120 up here, and when you hook them together, there's going to be a big spark between them, and it'll fry your electronics. So what you do is you ground them both, and when they're both grounded, now they both have the same spot that's 0, and so when you connect them, they won't spark.
Wait. Why do you have-
That's why in electronics, ground. Okay? That's why you have a ground on these things for electronics, is because it allows you to connect different electronics together without worrying about spark in between.
The ones that are dangerous.
Okay? That's one of the reasons. Others for safety. Okay, 2 more things you need to know.
Spark's not dangerous at all.
V, What's that? A voltmeter. Voltmeter. It measures potential difference. Everybody write this down. Okay, everybody? Plus, minus. It measures the difference between the two sides. So write this down. A voltmeter measures the difference between the two leads, or the two sides of the voltmeter. Okay?
Nice, but different.
Okay. Voltmeter, yes. So it's just voltmeter. Okay, measures the difference between the two sides. Okay, that's important. So you might want to put a delta V there, even if you want to remind you. Okay, and then this one, A. Okay, it's not an amp meter and it's not an ammeter. It's an ammeter. Ammeter. I know everybody wants to say amp meter, or occasionally you stutter and say ammeter, but it's just ammeter. Okay, now for this one, everybody, I want you to draw this little helper for you. Your little helper is this. It measures the current that goes through. Okay? So the only way for an ammeter to measure the current you want is to force the current you want through it. Okay? So it measures the current that goes through it, whereas a voltmeter measures the difference between the two sides. Okay? So it takes the potential on one side, the potential on the other side, and subtracts it. Okay? Alright, so here you go. In order to produce a circuit, here's what you must have. Number one, to produce a continuously operating circuit, you must have an EMF source.
And wire.
You must have a closed conducting path. Okay? Closed conducting path. And number three is you will always end up with some resistance. Okay? So a device or even internal resistance. There you go. There's your closed conducting path.
In reality, the wires are just there.
Now, everybody,
It must be alive.
real quick. In Physics B, unless otherwise stated, what's the resistance of our wires? Zero. Could wires in a problem have resistance?
Yes.
Yes. But if they don't give you the resistance of the wire, you assume the wire to be zero. Okay? Alright, so here, first things first, will you draw a circuit that will operate, that will turn on two light bulbs? Go. Okay, so here you go, because the question has popped up. Okay, somebody go to the board, draw me a circuit that turns on both bulbs, and then I want somebody else to go to the board, draw me a circuit that turns on and off only one of the bulbs. Right? Okay.
You should list everything to
Are you doing something
make you
amazing?
thirsty.
Oh, I'm sorry, it's because I was sick and my throat is...
No, you always have a drink.
Oh, I do anyway. It's true.
Fail.
It won't turn that one on, but
Alright,
the other one will always be on.
Yeah.
Well, oh wait,
No,
yeah.
they will turn off.
okay, let's start back here.
Because,
Yeah, I wouldn't do it.
Alright, back here, David's.
Doesn't work.
That doesn't
Both of
work.
them work.
Okay,
Both of them work.
David's
Those are the same.
has a... Does he have an EMF source?
Yes.
Does he have a closed conducting path?
Yes.
Does he have a switch?
Yes.
Okay, will it turn both bulbs on and off?
Yes.
Yes. Alright, so David's is correct. Alright,
Melanie.
You're supposed to have one turn on and one turn
Use
off.
an adjustable,
See?
Yeah, they
Okay, hang on. Alright, Melanie. Okay, we got EMF, we got conducting path, we got switch. Okay, wait, you saw nothing.
Censored blue screen.
censored blue screen.
Sorry, we're having technical difficulties.
technician difficulties, you mean?
Will that work? Will that work? Will this work?
Yes.
Okay, so now, let's follow the current.
I don't know, hook it up to something.
The current's going to flow this way, right?
Of course.
And then what?
Yeah, well,
Up, because it's got no place else to go, and then what?
It's fine.
That way, then what?
When the switch is on, it'll go
Okay,
right
when the
and
switch is up, what's it gonna do?
down.
It's gonna go that way, so this one stays on all the time.
Uh-huh.
Okay, close the switch.
Then it goes straight through.
Okay,
No,
so
it
some will go this way, some will go this way, and so then
technically-
both will be lit.
Technically, since it's a short and it has zero resistance, would it not go
All of
through?
it would go through.
Yeah, technically all of it goes through, right?
So use better. All the current will be forced.
All, yeah.
Oh,
Zero resistance.
excellent point.
Potato salad.
Now, if you were an electron, actually you're a proton because we're doing conventional current, and you are a proton and you come up to this spot and you say, look, they close this switch, which way do I want to go? Do I want to go through the very troublesome coil in this bulb, or do I want to go this way,
Yeah,
the superhighway?
the highway.
The answer is superhighway. Will any of them pick this way?
No.
Okay, this is called a short.
Well, since it has no resistance.
Actually, it's called a short for shortcut. It's actually a short circuit because there's no resistance in it. So in this case, when you close this switch, that one still won't go on. How can we change it?
Just put the bulbs in on, put the bulb on the short circuit and put the switch before it.
Yeah.
You could put a resistor, or you
Move the bulb on the left to the short circuit. Yeah, that.
and then move your switch.
Actually, the switch right here should be.
This will do it. Okay, if you go back there, David has drawn it. What I drew right here is the same as that one. All right, next time. Okay, hang on, sit down. You're insulting me by putting everything up. Thank you. All right, now, here's the deal. Next time, what we will do is we will continue with circuit drawings. We will talk about Kirchhoff's rules,
And KC.
junction rule, actually the current rule, and the voltage rule, which are conservation of charge and conservation of energy. Okay? And we'll see their implications for different types of circuits, both series and parallel and combination circuits. That's as far as we'll go in this class. So we won't do any strange circuits that are not one of those three.